In this module, we shall discuss synthesis of cam profile, that is, determination of cam profile to generate the desired follower motion. We have already seen that the motion of the follower is described by the movement or displacement of the trace point. It can be described as a function of the cam rotation theta, y the displacement of the trace point as a function of theta. This is given to us, that is the desired motion. It can be given either in this analytical form or in the form of a displacement diagram if we go for graphical synthesis. It is known that this theta is measured from the beginning of the rise, that is at theta equal to 0, displacement of the follower is also 0, and at theta equal to theta Ri, that is at the end of the rise, the displacement of the follower is the lift. Now, we shall restrict our discussion for translating follower. To start with, we restrict our discussion for translating follower. However, before we get into the discussion of cam profile synthesis, we shall see that to produce this desired motion of the follower, we cannot come out with an unique cam unless we determine some basic dimensions of the cam. So, we first say we determine the basic dimensions. Basic dimensions of the cam, as you will see, one is the base circle radius, RB. We have to first determine what must be the base circle radius, that is the size of the cam. And we have also to come up with what is the proper offset of the follower, which we denote by E. This is the desired motion of the follower. We have accepted the follower to be a translating type, but before we come up with the cam curve, that is the cam profile, we have to first determine what should be the base circle radius of the cam and what should be the offset of the follower. However, it is obvious that we should always go for minimum value of the base circle radius, because smaller the value of RB, smaller is the cam size. With increasing RB, the cam size also increases. Our objective will always be to use the minimum value of the RB that we can use. However, we cannot choose this RB minimum arbitrarily. Let us see minimum value of RB, which we call RB min. The minimum value of RB is decided by various considerations. For example, one is, suppose we are talking of translating follower, we talk of a flat face follower. Now, this minimum value of RB of a flat face follower will be governed by what is the minimum value of the radius of curvature of the cam profile. So, we say rho min, where rho is the radius of curvature of the cam profile. The cam curve will have different amount of radius of curvature at different points, but we cannot take the radius of curvature of the cam profile below this value of rho min. For example, for a flat face follower, it is obvious that the cam profile has to be concave, which means rho everywhere must be positive, greater than 0, curvature is positive, so rho min must be greater than 0. That is not all. In fact, just 0 is not sufficient. because as we will see, when two surfaces are in contact, suppose this is the flat face and this is the cam surface. Now, the stress here at this contact zone, which we call contact stress, is decided by the radius of curvature of these two mating surfaces. Like here, if this is the rho of the cam profile, and of course for flat face follower, this rho of the flat face is infinite because it is a flat surface. So, the contact stress will be decided by this radius of curvature. So, the allowable contact stress level for the given force, the allowable contact stress level decides what must be the minimum radius of curvature. We will not get into the detailed discussion of how to determine this contact stress and how does it depend on rho. What we shall assume that rho mean is prescribed. From this contact stress point of view, for a flat face follower, the rho mean of the cam profile is prescribed. Another consideration, we know that the eccentricity of the driving effort should not be too large, because then there is a chance of the follower to cock inside its bearing guide and jam in the follower. To prevent this jamming, we should also say what is the maximum allowable eccentricity of the driving effort, which we denoted by E. So, we also say E max is also prescribed. So, we are right now discussing a translating flat face follower. To determine the minimum value of the radius of the base circle and the offset that must be used, so that these two conditions, namely minimum value of the radius of curvature of the cam profile and maximum allowable value of the eccentricity of the driving effort, are not violated. So, in our subsequent discussion, we shall assume rho mean, E max and Y theta are all given to us. How do we decide what is the minimum value of RB and that of the offset for a flat face follower? So, our next task is to determine the RB minimum, that is the minimum value of the base circle radius, and the offset that we can use for a flat face translating follower when minimum radius of curvature of the cam profile and maximum eccentricity of the driving effort and the desired follower motion are all prescribed. So, these are to be determined and these are given. As we said that this is a flat face follower, this is a cam which is rotating in the counterclockwise direction, this is the base circle, this circle is the base circle and this is the base circle radius. The cam center is here. The camshaft axis, let me call it O2. This is the follower axis along which the follower translates, and this distance is called the offset in the positive direction for this rotation of the cam, and that is E. And this is the contact point. So the distance of the contact point from the guide axis, this is the eccentricity of the driving effort, epsilon. What is the lowest position of the follower? When the follower is in contact with the base circle. As we see, this is where the cam profile is in touching the base circle. So if we draw a tangent to the base circle, horizontal tangent to the base circle, this is the lowest position of the follower when this point S was vertical. So this is from the level from which the follower starts rising. So at the beginning of the rise, contact was here when that contact was along the vertical line. This line O2, so let me say S, O2S was vertical. The cam has rotated by an angle theta, and consequently the movement of the follower is given by this y, which is a function of theta. Now let us see this contact point. If I call it C, the center of curvature of the cam profile at C, let it be here, which we call OC. OC is the center of curvature of the cam profile at this contact point C. I draw it here, OC. Now, what do we mean by center of curvature or the radius of curvature? That for 3 infinitesimally separated time instant, the circle with center at OC and OCC as radius is same as the cam profile. So if I draw the circle with OC as center and OCC as radius, then this circle and the cam profile, 3 infinitesimally separated positions are same on the cam profile and in this circle. So we can say for 3 infinitesimally separated position, this OCC, which is the radius of curvature rho, does not change. So what we can see, what is the expression for this rho? That is this distance plus this distance plus this distance. This distance is y and this distance is nothing but RB. This is RB. If I join these 2 points O and OCC, and if I call this angle as psi, then we can write the radius of curvature rho is nothing but RB plus y plus this vertical height, that is RB plus y plus this vertical height. I can write O2 OC, this distance, sine of this angle, that is sine of psi minus pi by 2, plus O2 OC sine of psi minus pi by 2. Let me repeat. The radius of curvature at this particular instant when the cam has rotated through an angle theta, this angle we call theta, cam rotation, is this distance, which is O2 OC sine of this angle, and this angle is psi minus pi by 2 plus RB plus Y. Now this expression is true, rho does not change or O2 OC does not change for 3 infinitesimally separated time instants, which means I can differentiate this expression up to twice, once and up to twice, assuming rho and O2 OC to be constant, because these do not change for 3 infinitesimally separated time instants. So if I differentiate once with respect to t, what we get, let me first simplify it. I can write RB plus Y, this is minus sine pi by 2 minus psi, so that is O2 OC cosine of psi. Similarly, if I replace this cam by this circle, and this equivalence is true only for 3 infinitesimally separated positions. That is very important, as we learned during the equivalent mechanisms for equilibrium higher pair mechanisms for lower pair linkage. That radius of curvature is same for this circle and this cam profile. So I can replace this cam by this circle up to 3 instants. And now we see this O2, S and OC, they are not moving at least for 3 infinitesimally separated instants. So this angle theta plus psi I can write constant, and this relationship is not valid for all t, but definitely valid for 3 infinitesimally separated time instants. So I can differentiate these expressions up to twice, once and twice, holding this as constant and rho and O2 OC as constant. So this gives me theta dot d theta dt is nothing but minus psi dot, or I can write d psi d theta as minus 1. D theta dt is minus d psi dt, so d psi d theta is minus 1. Now here if I differentiate it once, as I said earlier, rho and O2 OC can be treated as constant, and if I differentiate with respect to theta, which is nothing but differentiating with respect to t, because theta is omega t, we can write dy d theta is O2 OC minus sin psi into d psi d theta, which is again minus 1. This is 0. If I differentiate, this is 0. So dy d theta, if I come to this side, I get O2 OC minus sin psi into d psi d theta, which is minus 1. So that gives me y prime, which I denote dy d theta. Prime denotes differentiation with respect to theta. So y prime I get O2 OC into sin psi. As I said, these we can differentiate up to second time. So if I differentiate again, we get y double prime is O2 OC I can treat as constant, O2 OC cos psi into d psi d theta, which is minus 1. So I write a minus sign here. Y double prime I can write minus O2 OC cos psi. And here we can see we've been able to express rho in terms of all other quantities. Rho is RB plus Y plus this is minus O2 OC cos psi. And minus O2 OC cos psi is nothing but d2y d theta 2, the second derivative of y with respect to theta. RB plus y, which is a function of theta, plus y double prime theta. So this is the most important relationship between the radius of curvature of the cam profile in terms of the base circle radius and the displacement function. This is decided by this y theta. This will tell us that rho is minimum when this quantity is minimum. They are changing with theta, both y theta and y double prime theta, and when this whole quantity is minimum, that is when for a given RB, rho is minimum. So that clearly tells us that minimum value of RB has to be given value of rho mean minus y theta plus y double prime theta. I have to calculate the minimum value of this expression. For a given value of y theta, I first find where, for which value of theta, y theta plus y double prime theta is minimum, and what is that minimum value. Then RB minimum for a given value of rho mean I can get from this expression. Okay? So you can see for any lesser value of RB minimum, when you add this, the value of rho will turn out to be less than rho minimum. So this is the RB minimum. From this figure, we should be also be able to determine what is the offset of the other quantity. We have already determined RB minimum when those are given. Now, given the E max, I should be able to find out what is the E. That is the offset that is desired. Towards that end, we already had an expression for dy d theta, that was y prime, which was O2 OC sin psi. This we already had. And let us calculate this distance, this horizontal distance, which is E plus epsilon. What is E plus epsilon? Where epsilon is the eccentricity of the driving effort, E is the offset of the distance of the follower axis from the camshaft. That is O2 OC cosine of this angle, which is O2 OC. Cosine of that angle is cosine of psi minus pi by 2, which is same as cosine of pi by 2 minus psi, which is same as sin psi. O2 OC is sin psi. And here we just now proved that dy d theta is nothing but O2 OC sin psi. So this I can write y prime theta. So epsilon is y prime theta minus E. The driving eccentricity of driving effort is governed by this y prime theta and the offset E. Now, maximum value of this takes place when y prime theta is maximum minus E. So the minimum value of the offset is y prime theta max minus epsilon max. this equation determines the minimum value of the offset that has to be used, so that epsilon never goes beyond this epsilon max, which is prescribed. We have to only see what is the maximum value of y prime theta. As you see, if any lower value of epsilon is used, then epsilon max will be more, because this is minus e. So this is the minimum value of offset. So we have got both the relations, minimum value of RB and minimum value of the offset. From here we can also get what is the phase width of the follower, this width of the follower phase that is necessary, because as you see the contact point is changing. Right now it is here, in some other instance it may be there. So what is the minimum width of the follower? To do that, as we see, this distance eccentricity of driving effort epsilon is given by y prime theta minus e. So when y prime theta is positive, epsilon is positive, this will be more than this, and the contact is on the right of this follower axis. And when y prime theta is negative, y prime theta minus e, which will be negative, that means the contact will be on the left of this. So total width of the follower that is necessary, that is maximum positive epsilon plus maximum negative epsilon. We have to take the magnitude of this value plus the magnitude of the positive value. So if I call that follower width, minimum follower width, that is epsilon positive maximum and plus epsilon negative maximum, and then I take the absolute value. Which is clearly seen that E cancels, and this will come out to be y prime theta max plus absolute value of y prime theta mean, which is negative. So I take the absolute value. So the total follower width, if I call it W, is given by y prime theta max plus y prime theta minimum, which is negative, take the absolute value, add up these two values, and normally we keep some allowance on either side. If the contact point comes up to here, I should keep an allowance here. Similarly, if the contact point comes up to here, I keep an same amount of allowance here. So 2 times some allowance which the designer can choose. So given this rho mean, epsilon max and y theta, we have determined RB minimum and the minimum amount of offset and also the minimum amount of follower width that is necessary for this cam follower system to function smoothly. Now we shall discuss how to determine the optimum values of minimum values of the base circle radius and the offset for a roller follower. So we are discussing a translating roller follower and we have to determine what are the optimum values of the base circle radius and the offset that is needed. What are given to us is the desired motion of the follower y theta and the maximum value of the pressure angle which can be allowed. The maximum possible value of the phi, that is the pressure angle which is allowed. As we know, during the rise of the follower, this angle is critical and it should not be allowed to go beyond a prescribed maximum. So phi max, let me say during rise, this is also prescribed, and rho mean of the cam profile, as I said in case of a flat face follower, is dictated by the contact stress point of view. But what we will do here, will satisfy this maximum pressure angle condition for a given y theta. I will determine RB and E, and once I get RB and for a given y theta, the cam profile becomes unique, and I can calculate what are the rho of that cam profile at various points for various values of theta, and we should only check that this condition is not violated. So what we will do for given y theta and phi max, how to determine the values of RB and E for a translating roller follower. Let us say this is the base circle radius, this is the camshaft axis, and as I said, the follower axis is offset. Let this be the follower axis. The roller center is here. This is the roller which is hinged to the follower. And as we see here, an extra dimension is necessary, that is this given roller radius. This is decided not from kinematics but from the force transmission point of view. What is the minimum size of the pin, that decides the roller radius. So we also assume that RR is also given. This is the amount of offset. The cam is rotating in the counterclockwise direction. So if this is the base circle radius, then I know if we drew the pitch curve, which is a curve parallel to the cam profile, and the distance between them everywhere is the roller radius. This is the prime circle. This is the base circle, radius RB, and this is the prime circle, whose radius RP is RB plus RR. And if this is the contact point, then joining the contact point with the roller center, that is the common normal between the cam and the roller surface, and it is this angle that this common normal makes with the direction of the follower movement is called the pressure angle. So first of all, let us try to get an expression for this pressure angle in terms of RB and other things. Now, what is the lowest point of the follower? When the follower roller, the trace point comes here, meets the prime circle. So this is the lowest point of the follower. So the rise of the follower at this instant is so much. This is the lowest point of the roller center when theta is 0, and when the cam is rotated by an angle theta, this is the displacement of the follower, which we call y theta. Now let us see what is theta. When the contact point was here, when this contact point was here, that is when the roller was at its lowest position, and now the contact point between the base circle, prime circle and the pitch curve is here. So this is the cam rotation theta. Let me call it O2. This is S prime. When this line O2 S prime was here, then the roller was at its lowest position. Now, to determine the pressure angle in terms of these geometrical quantities, I take advantage of the Aaron-Holt-Kennedy theorem. This is a mechanism, as we see, of 4 rigid bodies. The fixed link, that is 1, the cam is 2, the roller is 3, and the follower is 4. So it is a 4-link mechanism consisting of 1, 2 and 3, 4. Between 1 and 2 there is a revolute pair at O2, so this is also the relative instantaneous center 1, 2. 3 and 4 are connected by a revolute pair here at this roller center, so this is also the relative instantaneous center 3, 4. 4 is in vertical translation with respect to 1, so 1, 4 is at infinity in the horizontal direction. So we can say 1, 4 is in the horizontal direction at infinity. I can draw any horizontal line and 1, 4 lies at infinity because all parallel lines meet at infinity. So I can say if I draw a horizontal line through 1, 2, 1, 4 at infinity. So I have determined 1, 2, 3, 4, 1, 4. Now we also know 2, 3, that is between the cam and the roller, 2, 3 must lie on this common normal. I do not know where, but definitely it lies on this common normal. This contains 2, 3. Where exactly it will be located in this line NN, that will depend on the amount of slip that is taking place. But now let me apply the Aaron-Holt-Kennedy theorem that I know 1, 2, 1, 4 and 2, 4 must be collinear. This is 1, 2 and 1, 4 lies on this line at infinity, so this line must contain 2, 4. This is 3, 4 and 2, 3 is contained on this line, so we can write 2, 3, 3, 4 and 2, 4. These 3 relative instantaneous centers are also collinear, out of which I know 2, 3 is on this line, 3, 4 is here, so this line also must contain 2, 4. Contains 2, 4. So 2, 4 is contained on this line and this line also contains 2, 4. So obviously this point of intersection that decides the location of 2, 4. This angle same as this angle, which is phi. So let me name this point as say A. A is the location of 2, 4, that is the relative instantaneous center between the cam and the follower, because cam is 2 and follower is 4. Once I have located this 2, 4 at A, we can easily get the expression of this pressure angle phi. Let this vertical line intersects this horizontal line through O2 at this point, which we call B. And this roller center, let me call it C. So what we see that tan phi is AB divided by BC. If phi is the pressure angle, then tan phi is AB by BC. Tangent of this angle is AB divided by BC, where A is 2, 4 and B is the point of intersection of the guide of the follower with the horizontal line through O2, that is line joining O2 and 2, 4. Now let me see what is AB. AB is nothing but O2A minus O2B, and O2B is nothing but E. So I can write this as O2A minus E divided by BC. And what is BC? BC is this vertical distance, out of which this is y and this is square root of rp squared minus e squared. I see a right angle triangle here. Hypotenuse is rp, that is the prime circle radius. This distance is e, so this vertical side is square root of rp squared minus e squared plus y. That gives me BC. So BC I can write square root of rp squared minus e squared plus y theta. Now let me see what is O2A. I know if I consider this point 2, 4 as a point on body 2, whatever velocity I get, if I consider it to be point on body 4, I will get the same velocity because it is 2, 4. 2, 4 means these two coincident points on body 2 and body 4 have the same velocity at this configuration. So if I consider this to be a point on body 2, that is the cam which is rotating with constant omega, say constant omega d theta dt, then the velocity of this point is upward and the magnitude is O2A into d theta dt. So I can write O2A into d theta dt, that is the velocity of this point 2, 4 in the vertically upward direction. Now if I consider it to be point on body 4, that is the follower. As I know, the follower is a translating member, so all points on the follower have the same velocity. So this 2, 4, considering it to be point on body 4, it has a velocity which is nothing but the velocity of the follower, which is dy dt. So that clearly tells me O2A is nothing but dy d theta. dy dt divided by d theta dt gives me dy d theta, which I write as y prime theta, where prime denotes the first derivative with respect to theta. So thus we arrive at an expression for tan phi. And it is this expression from where we will be able to determine the required values of Rb and E, as I shall show you a little later. So let me write the expression. Tan phi is y prime theta minus E divided by square root of rp squared E squared plus y theta, where rp is the prime circle radius, E is the offset. Thing to note that because I have provided this offset in the correct direction for positive values of y prime, that is positive value of dy dt, when the follower is rising, the value of phi is reduced due to the presence of this offset. Without this offset, whatever value you would have got, by giving this offset, I am reducing the pressure angle. That is the objective of providing this offset. Now this expression we can use to get the proper values of Rp, and of course if I get Rp, I can get Rb and also the value of E. To do this, we take help of a geometric representation of this particular equation. Tan phi equal to I prime theta minus E divided by this, and you should also note that when y prime theta is negative, the phi value will increase. Of course, the value of phi is negative, but the magnitude of the pressure angle will increase due to the presence of this offset while the follower is coming down, that is during the return stroke of the follower. But as I said earlier, that does not matter. It is only during rise there is a chance of jamming of the follower in the guide, and I reduce the pressure angle by providing this offset. We have just now obtained this expression for the pressure angle phi as tan phi is y prime minus E divided by square root of rp squared minus E squared plus y. As I know, we have been given the desired displacement function y theta, which is a periodic function because it repeats after every 2 pi rotation of the cam. So, this is a periodic function. If it is a periodic function, then if I plot y theta along this vertical line and y prime theta along this horizontal line, then that will be a closed curve. I mean, the shape of the curve is unimportant, that will depend on the value of y, function y. Let us say this is the curve. I get a closed curve between when I plot y versus y prime. This is the origin, let us say O. Now, if I draw a line at a distance E, the offset, and take a point on this line which is at a distance Rp from this origin O, and if I call say this point C. How C is located? This vertical line is at a distance E towards positive y prime from this y axis, and OC is equal to Rp, that locates this point C. Now we see, if I take any point on this curve, any point means a particular point. This point corresponds to some value of theta. Now let us see that the angle that this line, say CA, A represents a particular value of theta. The angle that this line CA makes with the vertical is nothing but the pressure angle for that value of theta. How? If I drop a perpendicular, if I call this point B and this point, I need not say what is this angle. If I call it psi, then tan of psi is AB by BC. And what is AB? AB is y prime theta minus E. AB is y prime theta minus E. So, y prime theta minus E. And what is BC? BC is this vertical distance, which is nothing but y for the corresponding to point A, that is y theta. And what is this vertical height? That is square root of Rp squared minus E squared. This is again a right angle triangle. This hypotenuse is Rp, this horizontal side is